All right, guys, here we go. So I am here. I'm going to do the recitation for the 6 p.m. session. So one sec, I need to cut the audio on my actual stream. Okay, so I'm here. I'm going to do the recitation for the 6 p.m. session. Today we're going to cover the same things that were covered in the 4:30 session. So if you were already went to that one, there's no real need to come to this one. Just a couple quick things before we get started. I have a list of notes of kind of my introduction here. So we're providing these at both time slots. That's for ease for you guys. So whichever one is easier for you guys to get to, go to that one. We're doing that so attendance is kind of more evenly divided. So there's no reason to go to two of them. If you want to, great. If not, don't worry about it. We're going to post these on YouTube afterwards. The fast way to, yeah. So it'll take probably a day until they're all uploaded, but they will get uploaded there. By the way, if you want to ask questions, look at the announcement that was posted on Canvas to understand how to do that. And yeah, basically the process is you're going to go on Piazza, put the title and the date of the recitation in there, kind of ask your question, and then I'll get to it on stream a little bit later. Other things, homework 8 is due on March 30th. That's the sorting homework. We pushed it back a week. Homework 9, pattern matching, is out now and will be due April 6th. We'll have a Gradescope submission open for that in a second. And once you do that, you'll get, I think, an extra bonus point if you submit on there and as well as on Canvas. Keep in mind that the Canvas submission is the one that's going to be graded, but you'll get a bonus point for uploading to Gradescope too. Yeah. After that, also, this is like the test week. So what that means is that we're not going to cover any new material, but we are going to cover some of the older material and sorting that we maybe didn't get to in the last recitation or something like that. Also, we should probably have time at the end to review. So if you have extra questions like that, I'll kind of give you the notice once we covered everything for this recitation, and we can kind of touch on that stuff as well. So besides that, I have all the topics, over here on this side of the screen. I'm wearing my AirPods because this is like the best mic that I could find without me having to buy a new one. We have the chat TAs, Keely and Mitchell, and today's topics are right there. So I'm going to go ahead and move over to my whiteboard, and we're going to get started with cocktail shaker sort. Okay, cool. So I'm going to move over here, and we're going to go to cocktail shaker sort. So let's move my thing so I can see all the questions that might be here. Make sure that this is cool. All right, we're all good. So today we're going to talk about cocktail shaker sort. That's kind of going to be the first sort that we touch on today. So cocktail shaker sort is basically, the way that I like to think about it is it's kind of a variation of bubble sort, right? Whereas bubble sort, we take two different elements, we compare them. If the one on the left is greater than the one on the right, we swap, and we just continue to bubble that element all the way to the right. Once we're done doing that, basically, then now we have a sorted portion of the array over here, which had contained the greatest element from the last iteration, and then the rest of the unsorted section. And then we kind of bubble this way again. So cocktail shaker sort is basically just a variation of bubble sort in the fact that we're just going to do one forward iteration of bubble sort, and then right after that, we're going to go from that element that is the greatest element, we're actually going to decrement and go all the way back to the other end of the array, right? And by bubbling forward and then bubbling backwards, we're going to optimize in a couple of niche scenarios where bubble sort might have not done so very well. So then the prerequisite after I iterations is that the first I and the last I elements are in final sorted order. And that's kind of the same stipulation as with regular bubble sort, where at the end of one iteration for bubble sort, the last element is guaranteed to be sorted. Now, just since we're going to the right and to the left, that means that we have that same stipulation on both sides of the array. Cool. And when I say final, they're in their final sorted order. They are in their final sorted order. And what that means is the same as in bubble sort. After we have a set of elements that is in its sorted order, there's no reason to consider it anymore. There's no reason to do any more comparisons. So at that point, what we're actually going to do is we're not going to touch it at all, right? And I'll denote that in a second with my little example. So this means after I iterations, the first I and the last I elements don't need to be touched. However, we will still be using the last swap optimization actually in both directions. So that's not just in one direction like we were using before with bubble sort. We're actually going to use it going backwards as well. Kind of a extreme case of that is the fact of where we don't swap at all during an iteration. What that means is that actually the sort is completely complete. Because if we don't do any swaps in an entire iteration, that means that there's nothing left to be sorted. Cool. I talked about the optimization, and now let's just kind of go into a brief example. Then I'm going to probably move over to the visualization tool in a second. So over here on my whiteboard, you can see the green is going to denote equals done sorting. Basically, what's going to happen is that this is our unsorted array here. And so we'll have pointers over here to 2169. We're going to compare. We'll see if the one on the left is larger than the one on the right. If it is, we'll do a swap. If not, we keep on going. 21 is not greater than 69, so we continue. 69 is larger than 67. So what we're going to do is we're going to swap these two, and then we would compare 69 and 6. Swap these two again. And you can see that 7 and 6 and 69 are in their locations as well. From there, we're going to swap, or we're going to compare 69 and 94. 69 is not larger than 94, so we don't do anything. 94 is larger than 34, so it's going to swap. 94 is larger than 43, we're going to swap. And then 94 is larger than 78, so I'm also going to swap as well. Got a question? So for cocktail shaker, Landon said that after the ith iteration of cocktail sort, then the first I and the last I are sorted. With optimization, can we argue that cocktail shaker is approximately twice as fast as bubble sort? So I don't want to make that conjecture because I don't think that's true. You can't globally say that's true by any means. And we'll actually talk about their complexities in a bit. They're actually going to have very, very similar complexities, bubble sort and cocktail shaker sort. But I wouldn't go so far to say that one is twice as fast as the other. Although it is possible for the array to be more sorted than it would be the bubble sort because we're going a different direction and it can perform better in some edge cases. I'm not going to go too far to say globally cocktail shaker sort is twice as good as the other one. Thank you for that question, though. Good question. Okay, cool. So I got done with that iteration, and then I denoted that this was the largest element, 94 was, and that's why I underlined it over here with green. So then from there, there's no reason to compare 94. So instead of comparing 94 and 78, I'm actually going to compare 78 and 43, right? And so from there, I see, okay, 43 is less than 78. That's fine. I'll go ahead and compare here. That's fine as well. 34 is less than 69, so I'm going to swap, right? And I denoted that right here. This is going to be the result after that backwards iteration. Then from there, I'm going to say is 34 less than 6? It is not. So 34 is in its final space over here. Compare 6 and 7. 7 needs to swap with 6. So I denoted 7 right here. And then 6 compared to 21. 6 is also less than 21, so that'll be a swap as well, denoted by that swap right there. Right, so after one forward iteration and one backwards iteration, we're looking at 6 in its final location. It's the minimum element in the array. 21, 7, 34, 69, 43, 78, 94, with 94 also being its final position in the array. And this process is going to continue. The next iteration would then be in the forward direction, and the one after that would be in the backwards direction. And this kind of mimics the back and forth method. What we do is when we call it a cocktail shaker. Okay, so I'm going to go to the Viz tool, and we're actually going to do a example on the Viz tool to kind of help you guys out. Cool. Let me go to the Viz tool. So the Viz tool is set up. Awesome. I'm going to look for a second just to make sure that goes over on the actual stream. And it does. Yay. Okay, cool. So this is the same array as I was using before. So I'm going to kind of go mildly fast. So from there, I'm actually going to hit step forward. Cool. 16 and 7. That's going to be a swap. Boom. I swap. Go to 69 and 6. From there, I am going to swap again. Boom. 69, 94. 69 is not less than 94, so I don't swap. 94 is greater than 94 or 34, so I swap. Boom, like this. 94, 43, larger, so I swap. Continue to bubble 94 forward as so. That's also going to swap as well. And then now we see we're at the end of the array, and the 9 will now be in its sorted location, denoted by the green once again. So I'm going to start my backwards iteration of cocktail shaker sort. Compare 43 to 78. 43 is not larger, so nothing happens. I decrement, attempt to swap again, no swap. Here's going to be a swap, so 69 is larger. Boom. Then from there, I'm going to go 34 is 6 is also less than 34, so no swap there. 7 and 6, that'll be a swap, and 6 is smaller. From there, then I go down and I compare 21 and 6. 6 is also smaller, so I'm going to swap again. So now we're done with that backwards first iteration, and then now we'll see that 6 is now in its final sort of location. Cool. From there, let's see. Okay, 21 and 7, that'll be a swap. Cool. 21 and 34, no swap. 34, 69, no swap. 69 and 43, that'll be a swap. Boom, and that'll be the last swapped. There was a marker for that. And then 69, 78, no swap. So now what's going to happen after I hit the next key, the step forward button, is that actually, if I remember correctly, our last swap was at 43, right over here. 69 and 78 didn't swap, so that actually means they're in the final location. So now when I hit step forward, boom, those are also sorted as well. So that's kind of the last swap optimization I was talking about earlier. So from there, I'm going to go down. I'm going to compare 43 and 34, the largest two elements that are considered in the kind of the unsorted portion of the array. From there, I'm going to step forward again. No swap here. Bam, no swap at all. So what do you think is going to happen when I hit step forward? So this would be the edge case of where nothing swapped. And if I hit step forward again, boom, the entire array is going to be sorted, right? So those are kind of two instances of where the last swap optimization comes into play. One where partially more of the array becomes sorted, and then the last one is when now the entire array is sorted, right? So that's super cool. Okay, now I'm going to keep going through. So now we're done with cocktail shaker sort. Went a bit out of order, but that's okay. And now I'm going to go back to the whiteboard. We're going to talk about the complexities for cocktail shaker sort. So for cocktail shaker sort, I'm going to make sure it's being anal, but I want to make sure that this shows up as well on the, cool, that's there. I know this is a little bit saggy on one side. That's unfortunate, but it's okay. Okay, so now I'm going to go back and I'm going to talk about the complexities of cocktail shaker sort. I'm going to touch on that. So cool. Over here in the bottom, I have best, average, worst, place, stable, and adaptable. So first, let's talk about the best case. Well, the best case is actually when the array is sorted. In the best case, I'm going to turn my iPad just so I can see questions if I get any. The best case is when I'm actually passed in a sorted array. When I'm passed in a sorted array, well, that last swap optimization kicks in, and after bubbling all the way to the right, I realize that I haven't swapped at all. Thanks for answering the question of cocktail shaker sort. One sec, I have a question. I guess what I was trying to say was the number of iterations in cocktail shaker sort on average is half the number of iterations in bubble sort. Half of the iterations on bubble sort. You still can't make that conjecture. I think that while it may seem that way on the surface, and it's not worth going into a proof of why that's not true, that isn't quite true, right? Depending on how, we'll see, for instance, when we get to the worst case, and I'll reference this question again, but hopefully if I remember. But in the general case, that is not true, unfortunately. Okay, cool. So I'm gonna go back to this. The best case, what I was talking about before, is when no swaps occur at all. The last swap optimization comes into play. And then from there, since I didn't swap at all, the entire array is sorted. So that would be one linear pass through of the data. And so that we can know is the best case. And the best case of this algorithm is O of n, right? O of n right here. Boom. That's the best case. That's if no swaps are happen at all. So now we get to the average case, and this is kind of what I'm going to reference back that other question before. I'm going to say that bubble sort on average before also took n squared. It was also on average O of n squared. This is actually also true for cocktail shaker sort. While this is not, this is the instance of where they really, on average, perform similarly. Cocktail shaker in general performs a little bit better, but not quite to the point of being twice as good. So for similar logic, this is going to be O of n squared. Because on average, we're going to be doing n pass-throughs of the data. Going through the unsorted portion of the array, that's an O of n operation, and we're doing that operation for n elements. So O of n times n is O of n squared. Jacob referenced something earlier. The answer that he's looking for is there half as many iterations, but each iteration is twice as long, so it's the same amount of work. In general, you're probably going to be, yeah. So Jacob followed up with that question, and yes, well, I guess you're doing, on paper, it looks like half the iterations. Well, you're actually going forwards and backwards. So in general, it's the same amount of comparisons, and you're doing about an equal amount of work. Okay, oops, this average should be n squared. I got distracted. Cool. And then the worst case, right? We can also probably guess what the worst case is for this. It's going to be in the case of where I'm given a reverse sorted array, right? For every single time, that means that on the forward iterations, I'm going to swap that max element all the way over to the right side. And then from there, however, I am going to get some benefit on going backwards. I'm going to get that next element to bubble back a little bit. And that will, in theory, I think, have a little bit less comparisons. I'm still have to go through the data n times. And then I have to do that. A linear scan takes O of n, and then I have to do that for n elements. So that's also going to be n squared. Right, so now we're left with the worst case for cocktail is also O of n squared, unfortunately. Cool. Let's talk about the place. Place is pretty easy for cocktail sort. It's in place. There's no extra auxiliary data storage that's being allocated. So with that, we call this in place. Cool. In terms of stability, right? By this is the similar property it has to bubble sort, right? In bubble sort, we're only going to be switching with a strict greater than when we're comparing this element to the element on the right. If we still enforce that greater than in bubbles and a cocktail shaker sort, we can also kind of enforce the stability property, because if there were two duplicates, right? If this was a 13 and 13, then if I was doing strict inequality, then the 13 would not be greater than the 13 on the right, and they wouldn't switch, right? So I can enforce stability by having a strict greater than sign. So I'm going to write stability. It is, yes, it is stable. In terms of being adaptable, right? So with cocktail shaker sort. So with cocktail shaker sort, yeah, just making sure something. With cocktail shaker sort, yes, it actually is adaptable, and it's adaptable because of the last swap optimization, right? Because of, I just think of a quick instance of this is if we're passing in a fully sorted array and no swaps occur and the algorithm terminates, well, then that shows that the algorithm can adapt to pass in data that actually is already sorted, right? Because of the last swap optimization, we can say that this algorithm is adaptable. So I'm going to put yes for this as well. So I'm going to pause for a second for any questions on cocktail shaker sort. I'm going to move on to selection sort. Also, I'm going to check on my time. Cool, 15 minutes in. So yeah, I'm doing fine. I have time. I'll wait about 30 seconds. Actually, I'm not even going to wait that long. If you have a question, I'll answer it as I'm starting up selection sort. Cool. Boom. So now on to selection sort. So selection sort is probably the, I'll say, lamest sorting algorithm we cover in the course, but it's important. We'll talk about kind of the one niche use case that it's helpful for, and then go from there. So selection sort. Selection sort is going to select the smallest element or the largest element. This is just an implementation choice. That's why I wrote it over here with an asterisk. It's going to select the smallest or largest element in the remaining unsorted portion of the array, and then it's going to swap this element directly into its final position in the final array, right? So that means that, for instance, if I was going over here, oops, I didn't have a name tag for this, but I'll make one really fast on my sticky note. I'll put, oops, I actually did have one, but I forgot about it. Oops, I have one right here. Cool. So if I was doing this initially, then 31A would be my minimum. When I get to 55, 55 would not be smaller, so it wouldn't be the min. 76, also not smaller, that would be the min. 69, larger. 26 is smaller, so I would move the min over here, identify this as the min element. Now let's see, 31B is now less than 26. You go over here to 12. 12 is smaller than 26. I go over to 82. 82 is now less than 12. So what that means now is I'm actually going to swap 12 into its final location right over here, right? And you'll notice two things when I'm doing this. One is that now, since 12 is going to be placed over here, it's actually going to be in its final location in the array. And that's basically what we're doing in selection sort. We're taking from the unsorted portion of the array, which initially is, well, the entire array, and then we're taking that minimum element and we're placing it right at the beginning of the array. And now, well, if we took the minimum of whatever thing's left and we put that at the beginning of our unsorted portion, well, then that element is in its final location in the array. So I'm going to write over here, and I'm actually going to draw out what this array is going to look like after I do the swap. So the big thing I'm going to notice is that 12 is going to swap over here with 31A, right? I'm going to swap 12, 55. Notice that everything else in the array is actually going to stay exactly the same. 31B, 31A, and 82. And actually something we're going to notice here is that if you guys were paying closer attention, is that we actually had a big problem. What's that big problem, you ask? Well, by doing this long swap over here from 31A to 12, 31A actually went to the other side of 31B. And so it lost its relative ordering in the swap, right? So over here, 31B is now on a different side of 31A, right? Notice over here, they were on different sides. A was to the left. Now over here, A is to the right. And so by doing these long kind of swaps, we can't guarantee that we're not switching a duplicate from one side of the relative ordering to the other, right? And because of that, what that means now is that we can't really enforce the stability of the algorithm, right? And so we'll talk about that later. Okay, anyways, and then the last thing that I kind of skipped over to kind of do a mini iteration of selection sort was after the ith iteration, the front I or the back I, that's just depending on your implementation choice of either choosing the min element or the max element. For this one, we chose the minimum element to swap with. So the front I would be considered sorted after I iterations, right? And we can see that now. I'll note this with a little green mega Sharpie. Now 12 is in its final location. I'm never going to touch 12 again. And then for the next iteration, I would go through over here. I'd say 55 is the min, 76, 69, 26, the min like this. There'd be no reason to touch this 12 because it's already in its final location in the sorted array, right? Okay, so after getting through these bullet points, I'm actually going to go over to the Viz tool and do a little mini example there. All right, Viz tool time. Going back over here, I'm still on cocktail shaker sort. This and all right, cool. So now I'm going to go through this again. I'm going to step forward. It's looking for this minimum element. Cool. Now it's 31A. Still 31A. Move over to 26 after this. Yep. And then from there, now 26 is the min, as you can see. Let me just make sure that this is showing up on the other stream. Cool. Yep, it is. All right. Back up to here. I'm going to step forward. Now I have a new min. It's going to go over here to 12. Boom, I get to 82. That's not smaller. So now I've finished searching through the array. I'm actually going to swap 12 and 31. And now we can notice this instability right over here. Now with 31A actually crossed over 31B. And as soon as we notice that's possible, that breaks the stability of the algorithm, right? There's no way we can guarantee that it's stable, right? And that's the thing with stability, another side tangent, is that the thing with stability is that while it may not necessarily always break in every time two duplicates are in selection sort, they might be in the same relative ordering afterwards. The fact that we cannot guarantee it means that the algorithm is not stable, right? We don't know for sure, and that's why we called it an algorithm unstable. Okay, cool. So now we're going to go forward. 12 is in its sorted portion of the array. It's going to turn green. Nice. 50, or the red's tracking the minimum element. Right now it's 55. Still 55. Now it's going to go over here to 26. Boom. 31Bs. Smaller, smaller. Boom. Swap 26 and 55. I swapped with the first part of the unsorted array with our min. Now over here, I'm going to hit step forward, and this is going to swap. Oops, I'm moving my iPad just so I can see questions in case there are any. Cool. I'm going to go over to 12 and 26. Yep, so now 26 is also sorted, and now I'm going to go over 76 and 69. 69 is a new min. You can see that. Now 55 is going to be a new min. Cool. 31B also going to be a new min. Cool. 31A is not going to be a new min despite it being a duplicate because we're doing less than for the minimum element. That doesn't matter really. I'm going to go over here to 82. And 31B is not greater than 82. So 31B stays the min. And now I'm going to swap 31B over here with 76. 76 is the beginning of the unsorted section. I'm going to swap that with now the minimum element in the unsorted section. Boom. Keep on going. I told you, this algorithm is fairly lame. I'm going to go 69 to 55. 55 is the new min. Boom. 55 and 76. 55 stays the min. It'll swap now, or the min will update to 31A. 82 is not the min, so that's fine. I swap the two, right? Boom. Now all the green are sorted. I'm going to go from 55 to 76. 55 starts as the min, and it will stay the min for all these. 55 is going to kind of, quote, swap with itself, right? Now we'll see that 55 is now in the final sort location. Now we only have 3 elements left. 69 is the min of these. Now it's going to swap with 76. Now we're left with 2 elements. 76 is the min of these two. It's going to swap with itself, and then 82 is going to swap with itself as well. Yay, we're done with selection sort. Cool. I'm back over to the whiteboard, and we're going to go over to efficiencies. So get excited for that. Cool. Alrighty, I'm in my iPad so I can see questions if there are any. Oops, I did get a question. Oops, no, that was on a different channel. Lame. Okay, so right, I talked about all of these things earlier. I'm going to move my little min thing over here to the wall. Now I'm going to talk about the complexities of this algorithm. So another lame part of selection sort is its complexities, right? Let's think about it. So for every single time we're doing this algorithm, we're selecting from the unsorted portion of the array. We're searching through roughly n elements. And how many times are we going to do that? Well, n times. So O of n times n leads to O of n squared, right? So I'll put that as the average case. And then you're going to say, well, Landon, what if I pass in a sorted array? What if you pass in a sorted array? It's going to do the same exact thing. It will actually go through the entire unsorted select portion of the array. It can't tell the difference. It's going to see that the min element is actually at the beginning. The min element will swap with itself. And then from there, it'll go on to the next element. It'll go through all of these, realizing that this one's the min, swap with itself, and so on. Well, what's going to happen in that case? It's still going to be O of n times n operations, which leads to O of n squared complexity, right? So even in the best case, it's going to be O of n squared. And then obviously the worst case is also going to be O of n squared. So we see that, well, selection sort kind of seems not very good, right? In the best, average, and worst case, it's all O of n squared. That's not great at all. I will say, though, actually, I'll mention it after I talk about place stability and adaptable. In terms of place, one benefit of selection sort is that it is in place. There's no auxiliary storage. All I'm doing is I'm swapping elements in place. I'm not creating queues. I'm not creating a new portion of the array. That's not happening at all. So this is in place. Cool. Oops, that looks like a log end, a natural log. In place. In terms of being stable, well, I showed you earlier, because of 31A swapping over behind 31B, we can now say that this sort is unstable. It is not stable. So it's stable right now. I kind of already touched on that earlier, but I'm not going to keep on ragging on it. And then in terms of being adaptable, right? Well, we just saw that even if I pass in a sorted array, I'm still going to go through n elements. I'm going to do that n times, right? And that's if I pass in a sorted array. So selection sort actually has no way of realizing or identifying that it cannot identify when an array is sorted. And so because of this, we say that it is not adaptable. Nope. It is not adaptable, unfortunately, right? So that's not very good. It's O of n squared in all cases. It is in place, but it's not stable and it's not adaptable. So you may be thinking, well, why in the heck am I learning about selection sort? Well, there actually is one use case where selection sort actually performs well. And I guess it would be more of a circumstance than a use case. But think about a situation where in terms of writing the memory was very, very hard. It was very, very difficult, required more, it was an intensive operation. Well, the good news about selection sort is that each operation, or each time it runs through the array, one pass through the array, it's only going to do one swap, one and only swap. What that means is that it's doing one swap, and then it's going to do that n times. So I'm doing one swap every iteration. I do n iterations. Well, I'm actually guaranteed every single time exactly n swaps, right? And what that means is that selection sort is going to perform better than bubble sort, insertion sort, something better than some of the other naive sorts in terms of actual swaps that are performed. So if I was in some scenario where writing and reading a memory was very, very expensive, I'd want it to selection sort because I'd be doing the fewest number of write and read. I'd be doing the fewest number of write operations possible. Right, so that's the one use case of selection sort that's actually pretty good. Cool. I'm gonna take a second for questions as I get some water because my throat is parched. Cool. I don't see any questions, so means we're gonna go on to one of the more iconic algorithms in the course, Quicksort. So Quicksort has amassed the most amount of paper slides on my little easel over here. But I'm going to try and break it down to you in a way that's understandable and not too hard to understand. Those are the same thing. So with Quicksort, they're basically two different parts of the algorithm. The main part of the algorithm is the partition part of the algorithm. And this is actually similar, it's actually completely identical to the partition algorithm you talked about last week in terms of k-select. Literally the only difference of k-select and quicksort is that once I'm done doing partition and swapping the pivot into its final place, for quicksort, I'm going to call quicksort on either half, on both halves of the array, as opposed to in k-select, I'm only going to call it on the relevant side of the array, right? And that's because in k-select, I only care about one element, getting one element it's in its right sorted location, and get the element at a specific index for the entire array. But for quicksort, I actually want the entire array to be sorted, right? So for that, I need to call it actually on both sides. As opposed to k-select, I only cared about one side anyway, so the other side isn't going to benefit me, right? If I'm looking for the third element and my pivot swaps to number 5 or the fifth element, there's no reason for me to sort all the elements that are on the right side of the array, because if they're larger than the fifth element, well, they're certainly not going to be the third largest element in the array. Right? So I'm only going to call it on the smaller half. So it's a quicksort, I'm calling it on both halves. So still, I'm going to talk about kind of the mechanics behind quicksort. The first is kind of to choose a randomly selected pivot. When I randomly select a pivot, I'm going to randomly select a pivot and randomly select a pivot, swap to beginning of, right. I hate drawing them while I'm talking because I feel like I have to get out of the way, but I want to make a little note that as soon as I randomly select a pivot, I'm going to swap it to the beginning of the subarray, right? And that's important. We'll see that later on. After that, I'm going to do the partition part of the algorithm, which is generally the part where I feel like most people don't understand it as well as they could. So when we're partitioning the array, basically what we're going to do is that for any element, the elements of the pivot, our strategy to put that element in its final location in the array is to throw every single element that's larger on the left side of that element, and then everything that's less than that element to the left side of that element, and everything that's larger than the pivot, I'm going to throw it to the right side of the pivot's final location. And then when I'm done with that, if I swap the pivot back in, if everything to the left of the pivot, if everything that's greater than the pivot is to the right, and everything that's less than the pivot is to the left, so that means that while the pivot is less than everything on the right and greater than everything, or is greater than everything on the left and less than everything on the right, well, then that means that the pivot is now in its final location. Note that that doesn't mean that the left and right sides are sorted. They're sorted in the fact that everything to the left is less than, and everything to the right of the pivot, or everything to the right of the pivot is greater than. That doesn't necessarily mean that they're sorted, but for the pivot, that can place the pivot in its exact perfect location. Then after that, we're going to swap the pivot back into its final location in the array, and then we're going to recurse on the left side of the array and the right side of the array. So that means calling quicksort on two different parts of the array with different bounds, right? Cool. And handling basis cases appropriately. Generally, it happens at 0 or 1, and you would generally just like return in that scenario if it's a void return type. So I think it's best with quicksort to kind of go into an example, because these words don't really make a lot of sense until you've seen kind of an example. And I wrote similar notes here on partitioning. This is more in depth on the partitioning part of the algorithm. But what's happening here is that initially I'm going to swap the pivot to the front of the subarray. That's the random pivot that I've chosen. From there, I'm going to have a variable called I. It's going to scan from directly to the right of the pivot, and it's going to go until it hits something that's greater than or equal to the pivot. And it's going to keep incrementing until it hits that element. Then I have J. J does the opposite thing. It starts at the upward part of the bounds, and it decrements until it hits something that is less than the pivot, right? So these are both two while loops right here. And then the same while loops you'd see in k-select, for instance. So this would be like, while element at I is less than the pivot and inside the bounds, and this would be while the value at J is less than the pivot and inside the bounds. This I is generally going to increment, and J is going to decrement. So once this for loop breaks out, and that means that I is at an element that is now, I is going to be an element now that's larger, greater than or equal to the pivot, and J is going to be an element that's less than the pivot. This is kind of the throwing of elements that I mentioned earlier, is that I'm actually going to swap the elements at I and J. I'm going to swap the elements at I and J. What that means is I'm putting a small element throwing it to the other side, and I'm putting a large element that used to be over here back on the right side, right? And you're going to see that now by doing this, we're throwing small elements over there on the left side, and then we're throwing large elements over here on the right side, right? And we're going to see that later on, once I and j actually cross, now we're going to have the final location for where the pivot's supposed to swap into. So cool. Then I'm going to increment and decrement j after I've swapped them, because we'll clearly have dealt with the elements of those indices. There's no reason for me to want to encounter them again. And then I'm going to repeat doing this until I and j cross, right? So not only in this while loop are we looking while I is something that's less than the pivot, or like I is going to keep incrementing while I hit see something less than the pivot. We're actually going to stop if I is not less than j, or I is not, if I is ever larger than j, then we want to terminate the loop. And that's the same for this loop as well. As soon as I and j cross, we don't want to perform any more comparisons. At that point, we want to swap the two elements there. And keep in mind that I glossed over this, but I'm only swapping the elements at I and j, assuming that I and j haven't crossed. If they have crossed, I don't worry about that at all. I skip directly to the step over here where I swap the pivot with j, and now the pivot is going to be in its final location. I know that was a lot. I was probably talking fast. I tend to do that when I talk about Quicksort. You can start asking questions now if you want, but I'm going to go into an example of Quicksort first, and then we're going to do an example of the viz tool in a second as well. Let's look at my paper sorted out. Cool. So here's the starting array. I chose my random pivot. Just chose it to be a random element as in 4, or as in index 2 in this case, right? So this would be 1. Right. Cool. So these are just the indices. What's the first step? Well, the first step is I'm actually going to swap the pivot with the element that's at the beginning of our subarray. In that case, that's 7. So I'm going to go down here. I'm going to see. I'm going to go down here, and I'm going to see that 7 and 4 are going to swap. So I'm going to go 4, 2, 7, 5, 1, 9, 3, 6. I'm also going to check I'm doing on time. 6:37. Okay, I'm doing fine on time. Cool. So I swapped these two right here. Okay, from here, now I'm going to put I over here and then j over here. So notice that I put I at the beginning of my bounds, and it's going to be looking to go, it's looking to increment, and j is over here, and it's actually going to be looking to decrement. So what that's going to look like is that I is going to say, okay, I'm going to keep incrementing until I hit something that's greater than the pivot, right? So I'm going to rewrite this over here. 1, 9, 3, 6. So that means that I is going to look at 2. Is 2 greater than or equal to 4? No, it isn't. So I is going to increment over here. And then now I hit 7, right? Well, 7 is larger than 4. So I'm going to break out of that first while loop, and I'm going to go over to the j loop. Now where j is trying to decrement. Well, initially, j is trying to decrement. So then it sees initially is 4 less than, this is the pivot. I'll denote it here. I'm always comparing with 4 in this scenario. Cool. So I'm comparing, is 6 less than 4? No, it is not. J is going to decrement over here to 3. And then I'm going to compare, is 3 less than 4? Yes, it is. Right? So this would be the time where I'm going to break out of that second while loop. When I'm breaking out of that second while loop, now I've reached the case of where I has hit something larger and J has hit something smaller. And from that scenario, this is going to be exactly when I'm going to talk about throwing small elements to the left and large elements to the right. So these two elements over here are actually going to swap. Cool. So we're going to see this right here. 4, 2, 3, 5, 1, 9, 7, and 6. Cool. And now I'm going to increment I. I'm going to decrement J. I'm going to keep on our merry way. Cool. So now I'm over here. I'm doing the same thing. Now I'm at the back of the top of the overarching while loop. So now I see, okay, cool. What's going on here? I is looking for something that's larger than the pivot. Well, right now it's already at something larger than the pivot initially. 5 is larger than 4. So this loop is going to break out of this loop immediately, right? Because I has already hit an element that's larger than the pivot. Now I go over here to J. J's looking, and it's going to continue decrementing until it finds something smaller than the pivot, right? So what's going to happen over here? I'm going to redraw the array. 4, 2, 3, 5, 1, 9, 7, 6. J's going to go over here, and I's going to go right here. Boom, right? So now this scenario, the same thing is it's the same kind of scenario as above when we swapped. I has hit something that's larger than the pivot, and J has hit something that's smaller than the pivot. The two of them have not crossed yet, so I'm going to swap these two elements. Boom. 4, 2, 3, 1, 5, 9, 7, 6. And I'm going to increment I, and I'm going to decrement J. Okay, cool. Well, now at this point, right? Now at this point, just making sure, correct? Yeah, cool. So at this point, I'm actually not going to compare 1 with 4 to see if it's larger, because J and I have actually swapped, right? So as soon as J and I swap, I'm going to break out of that loop. I'm going to break out of the I loop as well. And now that that's the case, what's going to happen now, is that I'm going to break out of the loop and I'm going to swap with the thing that's at the pivot. I'm going to swap the thing at the pivot with J, right? So now J, we're going to swap, and we'll see once this is done. Boom, right? Now this is the pivot. This is our good old friend, the pivot. Well, now when we look at 4, we look at this and we say this, look, everything to the left half of 4 is actually smaller than 4. When we look at everything at the right, everything to the right is larger than 4. Well, that places 4. If 4 is larger than everything on the left and less than everything on the right, that means that 4 has to be in its perfect location, its final location. And now we can see that by throwing 3 to the left and throwing 7 to the right, we've swapped these two. We put a large element over here and a smaller element over here. The same thing with these two. And then it's basically resulted by throwing large elements or small elements to the left and large elements to the right. What we've done is we've had these two arrays that are more relatively sorted. This was just a convenient thing that 1, 2, and 3, this entire subarray happens to be sorted. That's possible, but it doesn't happen all the time. We notice over here on the right, 5, 9, 7, 6, those elements certainly aren't sorted, but all of them seemingly are, or all these are larger than 4, our pivot to begin with, right? So now what would happen is I've actually called quicksort, so I'm going to look at the note here, is everything is less than pivot. Everything over here is larger than the pivot. And what would happen next is I would call quicksort on the left part of the array and on the right part of the array with these new bounds being 0 and pivot -1, and the new bounds on the other side as well. And so by doing that, continually, what I'm going to do is I'm eventually going to be left with a sorted array. So I'm going to go over here to the Viz tool, and I'm going to go over it in a little bit more detail. It really takes a really long time to draw these out on the whiteboard, but I'm going to try and do it in the Viz tool. Hopefully it'll be a little bit clearer. Boom. And I forgot to change to the next tab from before. That's okay though. All right, quicksort. I'm gonna go over just make sure that this is correct on the stream. Cool, nice. So I'm gonna go back to this. I'm gonna change my iPad just so I can see questions. Oh, live registration questions. Okay, cool. So I'm gonna go back again. I'm gonna say, okay. I'm going to step forward. I'm gonna choose my random pivot. Notice how in the visualization tool, we've actually I don't know what it default does, if it picks the min element of the pivot or the first element of the pivot. We're about to find out. Step forward, 3 and 4. Actually, I'm going to restart this and I'm going to get the number. I'm going to make sure I set it to pick the first element of the pivot. Okay, cool. So now it's going to be choosing the first element as the pivot. So that pivot is going to quote unquote like swap with itself. What that means now is that I is over here at 2, J is over here at 6, and same thing's going to happen. I is looking for something larger than or equal to, and J is looking for something that's less than. So first I'm going to go to the increment part of the loop. Boom. Now I is something that's larger than the pivot, so it's going to stop. And now it's going to break out and go into the J loop. J is looking for something that's smaller than the pivot. Well, 3 is less than 4, so it's going to stop right there. So now we've broken out of both loops. Now, since I and j have not crossed, we're going to throw the 3 to the left side of the array and the 7 to the right side of the array, just like that swap I was talking about earlier. Now I'm going to increment I and decrement j, just like as so. Now I is looking for something larger than or equal to the pivot 4. Well, it already hit one, 5. So that loop's going to terminate. It's going to go now to the j loop. J is going to look for something that's smaller than the pivot. It just did that. It hit 1. So now 1 is less than 4, and 5 is greater than 4. So I and j have not crossed yet, so this swap is also going to occur as well. Right, boom, these are going to swap. And now we're going to see that after I and j increment and decrement, boom, they've passed each other. And this is the exact instant where all the loops should break out and I should swap 4 into its final location over here at j. Notice how there's no reason to compare after this point. I don't perform any more comparisons. I stop the instant that I and j cross. And I'm going to swap j and pivot. Now 4 is in its final location. That's going to look exactly like the board did before. And now we're going to call quicksort on the left portion of the array first. Boom. So now 4 is sorted, right? It's going to go over here to the unsorted portion of the array. So this is me calling quicksort on the left portion of the array. From there, I'm going to randomly choose a pivot. Randomly, it happens, I set it to be the minimum element, or the first element being a pivot every single time. So now once the pivot, I is going to start at 2, and then j is going to start at 3. Boom, just as so. I is looking for something that is larger than the pivot. It just hit 1. So it breaks out of the loop, and now j is going to look for something that's less than the pivot. Boom. 3 is not less than 2, or 3 is not less than 1. 2 is not less than 1. It's actually crossed right here. So now j is now pointing at 1. So now I'm going to break out of that loop, and now I'm going to say, okay, 1's basically going to swap with itself. Boom. Okay, so now if I recurse to the left, that would be there'd be no reason to recurse to the left because I'm at a case of 0. There's no elements over to the left of the sort. So that'd be an implementation choice. Probably you would pass in the bounds and you would check that the a bound would be less than 0. Then now I'm going to recurse on the right side of 1. I'm going to recurse on this portion of the array over here. 2 and 3. Boom. I select 2 as my pivot. I and j are both going to happen to be the same number, 3. So I is going to look for something that's larger than the pivot. It already has. So it's going to break out of that loop. And then j is going to decrement until it finds something less than the pivot. Well, that's going to be 2. Now the loops are going to break out. 2 is going to swap with itself. Boom. And then now all we have to do is recurse on the right side of 2 onto the 3 right here. Boom. This 3 now is going to be now this 3 is going to be sorted. It's an element in subarray of 1, so that means it's sorted as well. And now I'm finally going to be able to return to that recursive call of quicksort on the right half of 4. These elements all the way over here. I did the recursive call on the left first, and now all of these recursive calls have terminated, and now I can finally recurse on the right side of 4 over here. So I'm going to step forward, and now 5, 8, 7, and 6 are going to be my subarray. The pivot is going to be 5, the first element, conveniently, the quote-unquote random pivot. I is going to be initialized to 8, the right above the pivot bounds. And 6 is going to be, cool, I got a question. Okay, the question is, why did Landon say I scan from right of the pivot until hitting a value greater than or equal to pivot, and then J scans from left to pivot until hitting value less than the pivot? Aren't both I and J scanning to the right of the pivot, so the pivot is the 0th index? Oops, I may have misspoke. What I meant to say is that I is going to the right. Well, yes, both of them are to the right of the pivot because it's at the 0th index. I is going to be incrementing, and J is always going to be decrementing. And that's what I meant to say. I shouldn't have put a pivot there because you're technically correct. But in general, I is going to be moving. It's always going to be incrementing, and J is always going to be decrementing. So that's my answer to the question. Shouldn't have said pivot, but, minor verbal diarrhea on my part. Okay, cool. So now 5 is the pivot. I'm going to step forward. Now 8 is initialized to be I. 6 is initialized to be J. I is going to look for something that is larger than the pivot. Well, it already happened to hit 1, and it's going to break out of that loop. as we can see. Yep. And then J is going to look for something that is less than the pivot. What do you think's going to happen here? Nothing is less than the pivot. Wow, shocker. So now I and J have crossed. I'm going to break out of all the loops, and I'm immediately going to swap the pivot with J. Notice that J happens to be exactly at the same index, so they quote unquote swap with itself. 5 is going to swap, and then I'm going to recurse on the left or the right side of the array. Cool. Now 8 is the pivot, and then 7 is going to be initialized to I. J is going to be initialized to 6. From there, what's going to happen is that 7. What's going to happen there is that 7 or I is going to look for something that's larger than the pivot. I is going to continue to increment. 6 still is not larger than the pivot. Boom. So this is a case where we have to be very, very particular about not comparing once I and J have crossed, because in this case, I has actually crossed beyond the bound of the array. So we want to perform a comparison here because then we get an array index out of bounds exception. So notice that I and J have crossed. So at this point, I'm actually going to swap the pivot with J. Nice. And then now notice that everything to the left of 8 is less than it. Notice that conveniently they happen to be sorted, but they might not have. That was just a convenience sake. So I'm going to recurse on the left side of 8. 8's now sorted. I'm going to recurse on the left of it. 6 is initialized to the pivot. I and J are both going to be 7. I is going to terminate because it's something that's larger than the pivot already. And then J is going to decrement until it's something that's less than the pivot. I and J have crossed. So now 6 is going to swap with itself. Cool. And then now we get to another base case of 7. 7's only one element. A subarray of only one element is considered sorted. So boom. Now we're done with Quicksort. So by calling Quicksort recursively on the left half of the array and the right half of the array, each time what we're doing is we're putting one element in its perfect exact position. And by recursing on the entirety of the array, eventually the entire array, each element will be in its final sorted location. And at that point, when each element is in its final sorted location, the entire array is considered sorted. I still have a good amount of time. I'm going to go over to Heap Sort. I'll wait. I mean, if you guys have questions, feel free to still ask them. I'm going to go over to Heap Sort. And then with whatever time we're left, we can answer any questions you have about anything. That'll be perfectly fine. So I'm going to go over here to back over here to the whiteboard. Boom. And I'm going to get myself some water because my throat is also really dry. So the last sort we're going to talk about today is Heap Sort. Heap Sort, the newest sort in the 1332 list of sorts. Throat is really dry. I have to get some water really fast. Wow. Incredible. Okay. Cool. So let's talk about Heap Sort. Heap Sort, the last sort we're going to talk about today, in the newest addition to the list of sorts that we talk about in 1332. We're going to be talking about the out of place variant today. The out of place variant meaning we're going to be using a priority queue, a min heap, to store the elements in the array. There is an in-place version of Quicksort or of Heap Sort, which is covered all over the internet. All those implementations will be wrong if you were to do them for this homework, right? These are much more complicated and generally aren't very consistent. For this homework, we're actually going to ask you to do the out of place variant, which is way, 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 way easier to implement than the out of place variant is much easier to implement than the in place variant. I have a question though. Do we still recurse left and right even if one or both of the arrays, subarrays would be empty? Like in the case where the pivot was at the end 8 and we recurse left in one of those subarrays. So that's just a choice of how you want to, it's just a choice of convention. I would say that if the difference between the bounds is less than or equal to 1, I would just terminate that and return out of it. That's the best way to handle it, I think, is that basically you just check if the difference between the bounds is less than or equal to 1. If it's 1, it's a subarray of 1, and so it's already sorted anyways. If it's 0 or smaller than that, then there's no reason to. So I would say the recursive call, you would still call it on the left and right sides, but then it would immediately terminate. Or you could handle it when you're recursing on the left side and the right side. It's kind of up to you. Cool. And I forgot to talk about the complexities of Quicksort. I'm going to go back to the method I'm done with heap sort, just because I've already started with heap sort. Okay, cool. So for heap sort, just because heap sort's very, very easy. For heap sort, it's going to be like 5 lines of code when you're done. All you need to do is you're basically going to throw all the elements into a min heap, right? In Java, you can actually use Java's priority queue. So that's java.util.priority queue. And you can pass in a collection of data into the constructor. And that's why we actually pass in the data for this method as a collection. So it's very, very easy for you to literally just pass it in as an argument to the constructor in the priority queue. And from there, it basically performs build heap on that data in the priority queue. Now, when we have this priority queue, we have this min heap in a trench coat. Essentially, while the min heap is not empty, we're going to remove from the queue, and we're just going to place that element back at the relevant spot in the array. So, for instance, if I had, I'm going to do a small example. I'll do one right here. Ooh, I'll do my best. So I'm going to do 7, 9, 3, 4. Right, this is my array. Cool, and this is my priority queue over here. All I'm going to do is I'm going to throw all these elements into my priority queue. This is my collection of data. And then I'm just going to dequeue. I don't even know what's going on in the priority queue. I don't even have to know. It's going to dequeue the smallest element. All I'm going to do is I'm going to put that, place that in index 0. Then now the priority queue is still not empty, so I'm going to dequeue again. It's going to dequeue 4. I put 4 at index 1. Then from there, I'm going to dequeue again until I get 7. Put 7 at index 2, the next index in the array that doesn't have its correct sorted element. And finally, I'm going to dequeue 9, put 9 at that index. And now the entire priority queue is empty. And at that point, I would terminate the algorithm and then just return the array. I think it's a static method, so just don't do anything after that. So that's the process. While the min heap isn't empty, dequeue from the priority queue and place that element at the next spot in the array. So that's literally it. You're going to instantiate a priority queue, throw all the data into it as a collection, and then while that priority queue isn't empty, just continue to remove from the priority queue and place that element at the correct index in the actual array, and just overwrite whatever data was there before. And so this is extremely easy, and this is the out-of-place version of heap sort. The in-place version of heap sort, I don't want to talk about because I don't want to confuse you guys. You can look it up online if you want to. It's a lot more complicated. This is going to be literally 5 lines, and I know there aren't that many resources on it, but we're adding as an extra auxiliary method just to kind of test the bounds and show you guys kind of a use case for priority queues and heaps that we talked about earlier in the class, now when it comes to sorting. Okay, but very different from online implementations, to kind of stress that, because we get a lot of questions on Piazza about it. Okay, so heap sort, best, average, and worst case. So this is pretty easy. Basically what's going to happen is that initial time putting all the data into the array is going to take, that's actually going to take O of n time. It's going to take O of n time. And what that means is that, well, that means O of n time. And then after that, you're by dequeuing, how many times are you going to dequeue? Well, you're going to dequeue n times. And each time you dequeue, essentially you're performing the down heap operation, which is a complexity of log n. So every single time you dequeue, it takes log n, and you're doing that n times. So it turns out to be O of n plus n log n, which reduces to O of n log n, right? So I'm going to put that down here as the best. And spoiler alert, oops, n log n. Spoiler alert, this is the complexity for all 3 versions. Cool. So just to reiterate that one more time, throwing everything in the heap is O of n. Then I'm going to be dequeuing n times in total, and each time I dequeue, it's a log n operation. So it turns out to be O of n plus n log n. I get rid of the smaller, I get rid of n because it's smaller than n log n. N log n will dominate as n grows large, and then I'm just left with O of n log n. So that's left with our complexity in the best, average, and worst case. In terms of place, In terms of place, it is, as you could probably guess, out of place. I'm using an auxiliary data structure, being a priority queue, and I'm throwing all my data into that. So by doing that, and by throwing all the data into a priority queue, that is certainly out of place. I'm using more than O of 1 auxiliary storage. In terms of stability, generally because of the build heap algorithm and how Java's priority queue implementation is, we cannot guarantee that the sort is stable. So from that perspective, it is not stable. And that's because of when I'm initially passing that collection into the priority queue, there's no guarantee when it first performs build heap that where the duplicates are going to lie and which order relative to each other. When I'm dequeuing, there's no guarantee about it. So because of that, we say it's not stable. In terms of being adaptable, no, it's not adaptable either, right? It can't tell, even if I pass in a perfectly sorted array, it's still going to perform build heap, and I'm still going to dequeue every single time. It's going to be a cost of m log n. So in that case, we say that it is not adaptable, right? So out of place because of the priority queue. Stable, no, because of the build heap that's performed by Java's priority queue. And then adaptable, no. Nothing really changes no matter what kind of data you pass in. Because of that, we say that it is not adaptable. Cool. If you guys think of any heap sort questions, feel free to ask, but I'm going to go back to Quicksort and talk about its complexities. If I can find that paper. How am I doing on time? 7:01. Great on time. Cool. Okay. Now we're going to return to Quicksort to kind of go over the complexities. Sorry that I'm doing this after the fact, but I was just on a different page and I was 2 pages further and I forgot. Cool. So the best case for Quicksort is going to be, and this is kind of in the general case, and there are proofs that we'll talk about this later in your later studies. But basically, it's n log n, and I'll tell you why. I'll give you a brief explanation of why it's n log n. I don't like explaining it as much because Jacob does a better job explaining it, and this is actually the average case as well. Cool. Is that basically we're going through when we're doing the partition part of the algorithm, we're doing that, and that basically is going to be that's the cost of O of n, right, on whatever's left of the subarray. And then essentially, we're going to be doing that, assuming we get a good pivot choice, we're going to be doing that log n times. So if we're doing an O of n operation log n times, we're left with n log n for the best and average case of the algorithm. In terms of the worst case of the algorithm is actually in the fact where the pivot that we're choosing is the minimum element in that subarray. So that would be in the event of, let me go back over here to, oops, I have it right here. So that would be that in this scenario, instance 1 was selected as the pivot. Well, what basically happened is once I've swapped 1 with 7, is that I is just going to continue to increment all the way past here. Or actually, no, sorry, I is going to stay here. J is going to decrement all the way until it gets to that element, and no swaps are actually going to occur. And basically what that does is that it basically just performs a bad version of selection sort with recursion. And what happens is, I'll do a little mini demo of it down here. So this would be an instance I get, let me think, 3, 9, 1, 4, 2, 10. So let's say I swapped 3 and 1. I would be here, J would be here. So I is looking for something that's larger than the pivot. Well, it's already hit that. And now J is looking for something that is less than the pivot. So J is going to move all the way over here until it crosses. And it's right here. And now 1 is going to swap with itself, and then it's going to call Quicksort on the right portion of the array. It's going to call it on this bounds right here, right? And it's going to keep on, assuming that the pivot that's chosen actually is the minimum element every single time by poor random luck. What that means is I'm basically just performing selection sort every single time on every single iteration. And that devolves basically, if I'm doing an O of n operation now n times, this is actually going to devolve into O of n squared, right? So I'm doing an O of n operation in terms of partitioning, and I'm doing that now in a smaller array of n minus 1, n minus 2, or whatever. that summation is going to be n squared, right? And now we've arrived at an interesting thing in the course is where now the worst case for sorting algorithm is not based on the input array. It's actually defined by it's defined by the random pivot that is chosen for the algorithm, right? And you may just say, well, how can we just not ensure that we're not grabbing the minimum pivot every single time? Well, ensuring that it's not the minimum pivot every single time takes work to do that. There's some amount of work to decide, is this the min element in that portion of the subarray or not? The good news is that random things in general, as n tends towards infinity, the likelihood of you choosing the minimum pivot every single time is extremely low, exceptionally low, to the point of where this worst case of it being treated like selection sort almost will almost never occur, right? It's very, very unlikely. What's much more likely is that you get a pivot that's kind of relatively in the middle. And we'll say that in general, I'll write this over here, is that we want a pivot that's between the 25th percentile and the 75th percentile of that subarray, right? In a perfect world, we want a pivot that's the median, right, at the 50% interval. But actually, anything in this zone is considered a good pivot. And it's a good pivot because basically that means that there's enough of the data that we can throw to the left and throw to the right that we won't get into the scenario of this worst case selection sort. Wondering if there's anything else I can touch on that. I said that this occurs with the minimum, if the minimum element is chosen to the pivot. This is also true if the maximum element is chosen to the pivot. If, for instance, I had chosen 9 as the pivot instead, it'd be the exact opposite case. I would be looking for something that's larger than the pivot, and it would go all the way past to the right. It would pass. I would now be over here. It would swap 9 with the end, and then it would call quicksort on the left portion of the array. And I wouldn't have really done anything at all, right? So quicksort, the worst case is if the minimum or the maximum element is chosen for the pivot every single time. That's when we're going to result in an O of n squared case. Cool. In terms of place, not including the recursive stack, this is a in-place algorithm. Cool. There's no auxiliary storage. In terms of stability, because of these long swaps where I'm swapping data all the way past each other, like in a scenario where, let's look at this. Let's say that instead of this being, let's say that this was a 7a and this was a 7b, because I'm swapping 7a and 7b right here, and I'm swapping them past each other, what that means is that these two duplicate elements could actually be swapped and have their places swapped with each other. And with that, and I'll just draw it more clearly here. So this is 7b and this is 7a. Because you're doing these long swaps, you actually can't guarantee the stability of the algorithm. That's generally a telltale for these. That's generally a telltale for these sorting algorithms. If you're doing long swaps that aren't next to each other, you're generally not going to have a stable algorithm. So I'm saying this is not stable. No, not stable. In terms of being adaptable, unfortunately, quicksort is also not adaptable. If I pass in a perfectly sorted array, there's no way for it to tell that the array is perfectly sorted. If I were to pass in, 1, 2, 3, 4, 5, 6, whatever. Let's say it chooses 4 as the pivot. This is 4, this is 1. I is here, J is here. Well, what's going to happen is that I is just going to look for something larger. It's going to get over here. J is going to look for something larger. It's going to go over here. It's going to swap 4 and 1, et cetera, et cetera. It has no way of telling that the array that's passed in actually is sorted. And because of that, we say that the algorithm is also not stable. Nope, it's not stable. Okay, so that was all the material I was supposed to cover for today's recitation. What time is it right now? 7:09. I have 6 minutes. If you guys want to ask me other questions, I'll be happy to answer them. I'll go to a new thing on the whiteboard just in case you guys ask me something I need to write more. But besides that, good job, you guys, today. I don't know how many of you guys are still there, but this was fun. We're planning on doing this every week for these Corona recitations, and can't wait to see you guys later. I'll wait for a minute or two. I'm actually going to probably turn around, and unless you guys get a question, I'm just going to turn around, sit down, probably get some water. Just because I'm parched. Okay, cool. Let me go back to the introduction. Oops. All right, so I'm back over here. I'll wait and see if you guys have any questions. If not, no worries. And if not, I'll sign off here in a couple minutes. I've got to take down the pictures behind me, so you're lucky enough to enjoy some wall artwork, but I've gone through this entire Yeti in one recitation. That's how Thursday I am. It's brutal out there. Okay. I'll wait for a couple more minutes. Also, if you guys have comments, criticisms, feel free to leave them maybe as like a private note on Piazza, and I'll look at that later, just on feedback on what we could do to make this experience better for you guys, because at the end of the day, like, we want to make this experience as optimal as possible for you guys. So however we can do that is great. All right, I haven't got any questions. I'm gonna look at my phone. Silly people. Alrighty. I do not see anything else. All right, seeing, I'm gonna leave, maybe 60 more seconds. I don't really have anything to talk about. Just gonna close my, I'll do that later. Oh. I wore my 1332 shirt today just because I want to make it be a 1332 experience for you guys, the students. Jacob's gonna upload this to, we have an official 1332 YouTube channel. We're gonna use that. And hopefully in a perfect world, we'd like to timestamp the video with kind of the times of the questions we're answering. Oh, we got one. Thank you for doing so much for doing this. One note, is there any way to have a Blue Jeans meeting for questions? It's hard to type and listen and take notes. We can look into that. Yeah, we can get into it. I would say in the future, don't worry about losing the notes of me talking while you're typing your question, because this is going to be posted later. So you can easily just go back into the timestamp of when you stopped paying attention and started wanting to type your question, and you can go back and take notes on that. I would say it's more important for me to see your question, answer your question, just so that while I'm in front of you and I have all this set up or whatever. But of course, just for this recitation, if you weren't able to get all your questions out, you can feel free to schedule office hours with any of the TAs using the office hours calendar, and we can set up a Blue Jeans call with you there, and just to kind of talk about the complexities, maybe something that I missed or accidentally said wrong, like I did with that pivot thing earlier. But I really enjoyed doing this, guys. I'm probably going to sign off here in a second, and it was my honor to teach you guys now, and I'll teach you guys until the cows come home. So I'm going to sign off now, but it was great teaching you guys. And I will see you guys again next week at 4:30. So see you guys. Bye.